September 2020, the James Clerk Maxwell Telescope on the summit of Mauna Kea, Hawaii, was scanning the atmosphere of Venus as it had done hundreds of times before. But this time, the signal coming back did not match any existing model, phosphine, a molecule made of one phosphorus atom and 3 hydrogen atoms. That sounds unremarkable, until you understand that according to every verified chemical and physical model we have, phosphine has no business existing in the atmosphere of Venus at that concentration, no energy source large enough to produce it, no known inorganic chemical reaction capable of generating it, no explanation that fits the data. And here is what separates this signal from every other routine astronomical discovery. On Earth, phosphine is produced by essentially 2 sources. One is industrial synthesis in laboratory conditions under extreme heat and pressure. The other is biological activity, specifically anaerobic microorganisms, the kind of bacteria that thrive in environments completely devoid of oxygen. Venus has no laboratories, and for decades we have been confident that Venus has no life either. If that signal is real, and its origin cannot be accounted for by geology or any known abiotic chemistry, then only one possibility remains. One that mainstream science has carefully avoided stating directly for a very long time. This is not a story about a distant planet. This is a story about the razor-thin boundary between cannot exist and is already there. If you want to keep questioning the things you thought you understood, subscribe. But right now, let us get into it. Before we go any further, we need to dismantle something. The image of Venus most people carry in their heads, that soft, bright point of light hanging in the sky just before sunrise or just after sunset, is perhaps the most misleading picture in all of astronomy, because what that light is actually reflected from is one of the most hostile environments in the entire solar system. Let us talk about what Venus actually is. The surface temperature sits at 464 degrees Celsius. That is not a typo. That is hot enough to melt lead, hot enough to incinerate most metals we use in everyday engineering. Every single lander humanity has ever sent to the Venusian surface, without exception, was destroyed within 2 hours of arrival. Not damaged, destroyed. The atmospheric pressure at ground level is 92 times that of Earth. To put that in terms your body can feel, it is the equivalent of diving 900 meters below the ocean surface. The kind of pressure that does not just crush, it restructures matter. The clouds you see wrapping Venus in that familiar pale yellow glow are not water vapor. They are concentrated sulfuric acid suspended in layers between 45 and 70 kilometers above the surface. And those clouds move. Upper atmosphere winds on Venus reach 360 kilometers per hour, fast enough to circle the entire planet in just 4 Earth days, even though the planet itself rotates so slowly that a single Venusian day is longer than a Venusian year. Near the surface, the carbon dioxide atmosphere becomes so dense under that crushing pressure that it enters what physicists call a supercritical fluid state, no longer purely a gas, not quite a liquid, but something in between. Imagine trying to move through air that has the density of water, heated to 5 times the temperature of a kitchen oven. This is the world where phosphine was detected, not in some gentle temperate corner, not at the surface, but suspended in the cloud layers above, where remarkably, temperatures drop to a range between 0 and 90 degrees Celsius, where atmospheric pressure approximates that of Earth at sea level. Which raises a question that changes everything. What if the most relevant layer of Venus was never the surface at all? Let us be precise about what was actually found, when it was found, and what the data has done since, because the story of this evidence is almost as strange as the evidence itself. In September of 2020, Professor Jane Greaves of Cardiff University and her team published a paper in the journal Nature Astronomy. Using observations from 2 separate telescopes, James Clerk Maxwell Telescope in Hawaii and the ALMA array in Chile, they reported detecting phosphine in the cloud layers of Venus at an estimated concentration of around 20 parts per billion. The signal appeared at an altitude of approximately 53 to 61 kilometers above the surface, right in the middle of the temperate cloud layer we just discussed. The scientific community did not celebrate. It interrogated. Within weeks, independent research groups began reanalyzing the raw data. By late 2020 and into 2021, several teams concluded that errors in the original data calibration process had inflated the concentration estimate significantly. When corrected, the figure dropped to somewhere between 1 and 4 parts per billion. NASA declined to confirm the finding. The initial excitement gave way to serious skepticism, and for a period, it appeared the story might end there, a promising signal, quietly revised into ambiguity. But it did not end there. In 2023, Professor Greaves presented new findings at a major scientific conference. Fresh observations from the James Clerk Maxwell Telescope once again returned a phosphine signal, this time detected deeper within the Venusian atmosphere than before. A different altitude, a different dataset, the same molecule. Now here is where the chemistry becomes important, because this is not a debate about telescope calibration. This is a debate about what phosphine physically requires in order to exist. Phosphine is what chemists call a reduced phosphorus compound. Producing it requires significant energy input, specifically conditions that actively resist the oxidizing environment that dominates Venus's atmosphere. Sulfuric acid, the primary component of Venusian clouds, is among the most powerfully oxidizing substances known. It does not passively coexist with phosphine, it destroys it. Any phosphine present in those clouds is being broken down continuously, which means whatever is generating it must be doing so on an ongoing basis to maintain even a detectable concentration. This is the concept scientists refer to as chemical disequilibrium. Think of it this way. Imagine you are pouring water into a bathtub that has the drain wide open. If the water level stays constant, something is actively running the tap. The drain is the sulfuric acid. The water level is the phosphine concentration. And the only question that matters here is what is running the tap. On Jupiter and Saturn, the answer is clear. The crushing pressures deep within those gas giants force hydrogen and phosphorus together through purely mechanical means. Venus has no such interior conditions at cloud altitude. Lightning was proposed as an alternative source, but modeling studies showed that lightning on Venus could account for phosphine production at levels thousands of times lower than what was detected, even at the revised estimates. Volcanic outgassing was another candidate. And this one carries more weight than it might initially seem, because we now have evidence drawn from reanalysis of Magellan archival data published in 2023 that Venus may still be volcanically active today. But even accounting for that, atmospheric chemistry models cannot trace a credible pathway from volcanic phosphorus emissions to stable phosphine concentrations in the cloud layer where the signal was found. Every conventional explanation has been tested. Each one falls short of the data by orders of magnitude. What remains is not a conclusion, but it is a problem that refuses to be dismissed. There is a particular kind of discomfort that settles over a scientific field when the data refuses to cooperate with the theory. It is not dramatic. It does not announce itself. It arrives quietly, in the form of a number that does not fit, and it stays there, patient and immovable, while researchers try every available tool to make it go away. That is precisely where Venus science stands right now. Let us walk through the three most serious abiotic explanations that have been proposed and examine exactly where each one breaks down. The first is lightning. Venus does experience electrical discharge activity in its atmosphere, and under the right conditions, lightning can drive unusual chemical reactions. Researchers ran the numbers. Even under generous assumptions about the frequency and intensity of Venusian lightning, the maximum phosphine output falls short of the detected signal by a factor of thousands. Not slightly insufficient, fundamentally, categorically insufficient. Lightning is not the answer. The second is volcanism. This one deserves more respect as a hypothesis, because the volcanic picture of Venus has grown considerably more complex in recent years. The 2023 reanalysis of Magellan data identified surface changes consistent with active lava flows during the probe's operational period in the early 1990s. Venus may be volcanically alive today. But here is the problem. Phosphine produced at depth by volcanic processes would need to survive the journey upward through an increasingly oxidizing atmosphere before reaching the cloud layer. Atmospheric chemistry models consistently show it would be destroyed long before arriving at the altitude where the signal was detected. Volcanism delivers the molecule to the wrong place. The third is unknown chemistry. This is the most intellectually honest of the three, and also the least satisfying. Venus's cloud chemistry is genuinely complex, and there are compounds and reactions within those sulfuric acid layers that remain poorly characterized. It is possible, scientists would say this openly, that some undiscovered abiotic reaction pathway exists that could produce phosphine at the observed concentrations. But proposing unknown chemistry as an explanation is not an explanation. It is an admission that current models are incomplete. Pause here for a moment, because this is worth sitting with. In 1859, Urbain Le Verrier calculated that Mercury's orbit did not behave the way Newton's laws predicted. The discrepancy was small, a tiny drift in the planet's perihelion, but it was real, and it was consistent, and no one could explain it. For 56 years, it remained an open wound in classical physics. Then Einstein arrived with general relativity, and what had looked like an error in the data turned out to be a signal that the existing theory was simply not large enough to contain the truth. Sometimes the data is not wrong. Sometimes the framework is. Here is something worth sitting with before we go any further. Phosphine is being detected 40 million kilometers away in the acid clouds of a planet that would kill you in under 2 seconds if you were somehow standing on its surface. That is the scale we have been operating at. Planetary, astronomical, almost abstract in its remoteness. But the same molecule, the exact same molecular structure of one phosphorus atom, bonded to 3 hydrogen atoms, is being produced right now by anaerobic bacteria living inside your digestive system. The chemistry happening in the atmosphere of Venus and the chemistry happening inside your body at this precise moment are speaking the same molecular language. That is not a metaphor. That is biochemistry, and it forces a question that goes far beyond Venus specifically. If life, or something that produces the chemical signatures of life, can exist inside clouds of sulfuric acid at altitudes where pressure and temperature approximate conditions on Earth's surface, then the definition of a habitable environment that planetary science has operated under for decades is fundamentally too narrow. We have been searching for life by looking for places that look like Earth. Same temperature range, same pressure, same liquid water at the surface. But Earth-like surfaces represent an extraordinarily thin slice of the possible environments distributed across a galaxy containing somewhere in the range of 100 billion star systems. Consider what a broader definition means in practice. If atmospheric habitable zones are real, if life can anchor itself in cloud layers rather than on solid ground, then the number of potentially inhabited worlds in this galaxy alone expands by an order of magnitude we have not seriously calculated yet. You are made of the same atoms that were forged in stellar explosions billions of years ago. The phosphorus in your DNA, in your cell membranes, in the molecule that makes phosphine, it came from a dying star. Venus, you, the clouds 40 million kilometers away, all of it is the same matter, rearranged. The universe may be far less empty than we designed our search parameters to find. Intellectual honesty requires that we spend time here, in this part of the argument, before moving forward. Because there are serious scientists, not fringe voices, not contrarians, but genuinely accomplished researchers who look at the phosphine data and remain unconvinced, and their skepticism is not irrational. It is, in fact, exactly what the scientific method demands. Professor Sarah Seeger of the Massachusetts Institute of Technology has spent years developing models for potential life cycles in the Venusian cloud layers. She finds the hypothesis worth investigating. But even she has been careful to state publicly that phosphine is a suggestion, not a confirmation, a signal that demands explanation, not a discovery that provides one. The calibration problems that emerged after the initial 2020 publication were not minor. The original processing pipeline applied to the ALMA telescope data contained an error that, when corrected, reduced the estimated phosphine concentration by a factor of roughly 7. That is a significant revision. In science, a result that changes that substantially under reanalysis is a result that has not yet earned full confidence. There is also the uncomfortable reality that Venus's atmospheric chemistry remains one of the least characterized in the solar system. We have limited in situ measurements of the cloud layer composition. The number of unidentified spectral absorbers detected in the ultraviolet range alone suggests there are compounds present in those clouds that no model currently accounts for. An undiscovered abiotic source cannot be ruled out simply because we have not found it yet. All of this is true, every word of it. And here is the thing about all of it being true. None of it closes the question. Revised concentrations are still concentrations that require explanation. Uncharacterized chemistry is an open variable, not a resolved one. Skepticism about a hypothesis is not the same as refutation of it. The universe does not adjust its behavior to match our comfort level with the implications. It simply continues producing data, and the data, as of right now, has not been fully explained. Here is where the conversation needs to shift, because the question most people are asking about Venus may itself be the wrong question. Is there life on Venus? That is the headline. That is what gets repeated in science journalism, in podcast discussions, in comment sections. And that framing, while understandable, quietly narrows the scope of what this data might actually be telling us. The more precise question, and the more scientifically productive one, is this: what is Venus teaching us about the conditions under which life can originate and persist? Consider a hypothesis that has appeared in peer-reviewed literature, including the journal Astrobiology, developed in part by Professor Seeger's research group at the Massachusetts Institute of Technology. The proposal is not that life spontaneously generated in sulfuric acid clouds. The proposal is that Venus may once have had liquid water on its surface, a condition that current climate models suggest was plausible somewhere between 2 billion and 3 billion years ago, when the Sun was cooler and Venus had not yet undergone its runaway greenhouse transition. If microbial life emerged during that window, and if the surface subsequently became uninhabitable over geological timescales, then the clouds represent the last remaining environment on Venus, where temperatures and pressures fall within ranges that known biochemistry can tolerate. Life, in other words, may not have appeared in the clouds. It may have retreated there. This is a hypothesis. It is clearly labeled as such in the literature, and it should be understood that way here. But it is a hypothesis with a mechanistic logic behind it, not speculation dressed in scientific language, and it connects to something broader. Bacteria have been recovered from Earth's stratosphere at altitudes exceeding 40 kilometers. Life on this planet has already demonstrated that atmospheric environments are viable habitats. We did not predict that. We discovered it. The history of biology is largely a history of life existing in places we were confident it could not. Venus may simply be the next entry in that list, or it may not, but the question is no longer absurd, and that shift in itself is significant. The answers we are looking for are not going to come from telescopes alone. Every observation made so far, every phosphine signal, every spectral reading, every atmospheric model has been gathered remotely, interpreted through instruments that are separated from Venus by tens of millions of kilometers. What the science needs now is direct access, and that access is coming, though not as quickly as the question deserves. The most immediate prospect is the Venus Life Finder mission, a privately funded project developed in collaboration with Rocket Lab. Unlike the large flagship missions that require decade-long development cycles and congressional budget approvals, Venus LifeFinder was designed to be small, focused, and fast. Its specific objective is to send a probe directly into the Venusian cloud layer and test for the presence of organic chemistry and potential biological signatures in situ. As of May 2026, the mission timeline has faced delays, but it remains the nearest near-term opportunity for direct atmospheric sampling. Further along the timeline, NASA's Da Vinci mission, if it survives the ongoing budget pressures that have already claimed Veritas, is designed to descend through the Venusian atmosphere and characterize its chemical composition with a precision that remote observation simply cannot match. The data it would return on noble gases, chemical gradients, and atmospheric history would reframe nearly every current debate about Venus in a single mission. The European Space Agency's Envision orbiter, currently targeting a launch window in the early 2030s, will add high-resolution radar mapping and atmospheric spectroscopy to the picture. But here is the variable that no mission timeline accounts for: political will and funding stability. Veritas was already developed, already approved, and was suspended anyway. The gap between what science needs and what institutional budgets provide is not a technical problem. It is a prioritization problem. The universe has been patient with its secrets for 4.5 billion years. The only thing preventing us from accessing them now is not capability. It is decision. Slow down here for a moment. The history of science is not a history of answers. It is a history of questions that refuse to stay quiet. Penicillin was contamination in a petri dish that a less curious mind would have discarded. Gravitational waves were dismissed for decades as instrument noise before they were confirmed as ripples in the fabric of space-time itself. The phosphine signal on Venus may turn out to be a calibration artifact, an undiscovered chemical reaction, or something that rewrites the opening chapter of biology as we understand it. We do not know yet, and that is not a failure. That is precisely where science is most alive. What we do know is this: the cloud layers of Venus sit 40 million kilometers away, at temperatures and pressures compatible with known biochemistry, containing a molecule that our best models cannot fully account for. That is not nothing. That is a data point that has not been explained away, only disputed, revised, and persistently returned to. If the signal is real and the source is biological, then we are not alone, and the first life beyond Earth we ever confirmed would not be found in some distant star system centuries from now. It would be found next door. So, the question is no longer whether Venus deserves our attention. The question is whether we are paying enough of it.